Thanks. So it's my pleasure to introduce you to our first invited speaker for this year. So Amaury Hayat here. Amaury is a full professor at Ecole nationale des Ponts et Chaussées, and he's also part of Institut Polytechnique and a member of the Korean Institute for Advanced Studies. So Amaury obtained his PhD in 2019, quite young, at Sorbonne University, and he currently holds the High Paris, that's the way you say it, High Paris Paris Descartes Chair, where you worked on, I guess, AI models for mathematics and for mathematical research. And Amaury's contributions have been widely recognized. He received lots of prizes and medals, like the L.E. Rivot Medal and some European Embedded Control Institute PhD prize for his PhD. And he also nominated at the Forbes 30 under 30 Europe list. So today, he will share his perspective on the intersection of AI and LLMs and mathematics. So please join me in welcoming Amaury.
Thank you very much. Can you hear me well? Okay, perfect. So thank you, and I'd like to start by thanking the committee for the invitation. It's a great honor to be giving this first keynote of CPP 2026. And it's all the more humbling that just 6 years ago, I was working on problems like these ones in control of partial differential equations. So the hopes of being one day invited to CPP were relatively low. What's changed? What's changed is that 6 years ago, with a few colleagues who were working in a field that was called at the time natural language processing, we had a crazy dream that was shared by many researchers, and some of them are in this room. It was definitely shared also by several authors of science fiction. It was the dream of having an AI that could be trained to prove a mathematical result at least as well as a human, or even better. And we wanted to do this in a formal language. I'll detail why later on. So 6 years ago, there was no ChatGPT, there was no Gemini, and all these things that we know today. And so, as you can imagine, there were a kind of skepticism from the mathematical community. But things have evolved a lot in the last years, and we went from a computer scientist awareness of the abilities of AI models to a global awareness, mostly thanks to the arrival of ChatGPT. But in this global awareness, I include the scientists from other fields, because, for instance, today we are in a situation where the youngest Nobel laureate in chemistry in 70 years is primarily a computer scientist. So I believe it shows that machine learning techniques are changing the way we practice science, at least some sciences. And so it was a natural question, I believe, to wonder how is it going to change the practice of mathematics. And a big part of this question is, can an AI help mathematicians prove new results? So if you are a mathematician and you want to know if an AI can help you, I guess the very first thing that everyone tries is to ask a math question to a large language model, or ask it to prove a small lemma, or if you're working in formalization, ask it to formalize a small lemma. In any cases, if you were to try in 2022, 2023, you would most likely get terrible answers. But the models are evolving quickly, and if you try today with one of the so-called reasoning model, you may actually get answers that are useful from time to time at least. And for me, there was a threshold about a year ago where for the first time of my life, I gave a statement that I'm giving it to you completely out of context, but so the statement and the proof are not important. But I gave a statement to O3 at the time, and the proof, which is about twice as long as that, was completely correct. So of course, that wasn't an extremely hard lemma to prove. It's something I needed for a paper, and I guess it would have taken me 1 or 2 hours maybe, but in 45 seconds, I had the proof. And of course, I'm not the only one who experienced this. There are many other mathematicians who did, and more recently, for instance, you had Timothy Gowers saying that he crossed exactly the same threshold. He had a lemma that he wanted to show, and he gave it to GPT-5. GPT-5 gave the answer. But I think what's really interesting is to see that it's not necessarily a very hard lemma. It's something that he believes would have taken him about an hour. But at the end of the day, it still helps a lot to do it in 30 seconds. So this is about what I want to talk about today. I want to discuss how we got there, what's going to happen next. And so this talk will be in 3 parts. First, I'll give a general introduction on large language models for theorem proving. Then I'll discuss how we can improve these models by using reinforcement learning and why we should use reinforcement learning in particular when we're working in a formal language. And then I'll try to briefly give an example of how this can translate to software verification. All right, so let's start with the first part. So if I were to ask you to design a neural network that could prove a math theorem, well, I guess the first thing that everyone would like to try is to train a GPT model for mathematics. So something where you would give it a question, it will go through the GPT model, and hopefully you will get the proof at the end. So this is something that was tried for the first time by Stanislas Pollu and Ilya Sutskever in 2020. They called it GPT-F, so they were working at OpenAI, and they essentially based themselves on GPT-3, but they replaced the 3 by F for formal. This is because they use a lot of formal data. What's interesting to consider is that Ilya Sutskever, well, he's mostly known by the general public for being the guy who told Samad Mami was fired. But he should be, it's a pity, because he should be remembered for being an amazing AI scientist. And so just to say that at the time, already in 2020, there was a lot of enthusiasm from the machine learning community and from senior people in the machine learning community about these questions. So, okay, if we want to understand what's going on in here and how this can translate to mathematics, we need to go a little bit inside the GPT model. So as you probably know, at the center of ChatGPT, if I forget a lot of things, there is another regressive transformer. And the way an autoregressive transformer works is as follows, in a nutshell. Let's say that you have a neural network that is trained to predict, to autocomplete sentences. You would give it the beginning of a sentence. Thanks to this beginning of the sentence, thanks to the training, it's going to compute the density of probability of the next word, say. And then it's going to sample through this density of probability, and you get one word. And the autoregressive part is to actually put this back into the sentence and to do this again. Again, density of probability of the next word, sampling a word, and so on. And because this sentence, hope is a good thing, maybe the best of things and no good things ever die, is a quote from The Shawshank Redemption, which is a famous movie. I recommend if you haven't seen it. It's all over the internet, meaning that if you train your model on the internet, the more this sentence will look like this one, the more the density of probability will be spiked on one word, which is essentially the next word of this sentence. So this is how it works for language, and you can think, okay, let's do the same for math. You give it a math statement. It computes the density of probability of the next step of the proof, and then sample a step of proof, then put it back in the stack, and you do this again and again and again, and you hope that at the end of the day, you're going to sample something that says end of the proof, then your right column is the proof, and you hope that the proof is correct. Okay. So you can do this. But if you have access, if you're working in a formal language and have access to a computer assistant, this is a bit naive as a way of doing. You can do better. And the way you can do better is to do the following. You start by the same thing. You have a statement, compute the density of probability of the next step of the proof, so the next tactic to apply. You sample it. And then instead of just putting it back in the stack, you're going to really apply it to your state and see what's going to happen. For instance, you want to prove that cosine of x plus exponential of x is strictly lower than 1 plus 2 exponential of x. Your large language model tells you to apply this. So you apply this, and then your computer assistant is telling you that now you have 2 goals. So you did change the tactic state. Oh, sorry. So you change the tactic state, and you do this again and again and again, and you hope that at the end of the day, you have nothing to show. So the computer assistant will say nothing to show, and so here you don't even need a neural network. If you have nothing to show, you know it's the end of the proof. So in some sense, what you hope is that this algorithm will terminate, and if so, then your right column is the proof. So if you're doing this, the hope is that by showing it enough examples, the AI model will learn to reason just by predicting the next step of the proof. So you might be a bit pessimistic about it by thinking, if you want to do a good mathematical proof, it might be a bit short-sighted to only look at the next step every time. But on the other hand, I tend to believe that if you want to be good at writing an essay, you need to be better than just predicting the next word. And I'm forced to realize that ChatGPT is doing quite a good job there. So I could also be optimistic. Whether we're pessimistic or optimistic, this can only work if there is enough examples. And enough mean here sufficiently diverse and sufficiently numerous, and you really need a lot of them. And this is the main limitation. It's the main limitation because we have very few mathematical data available, especially in the formal language. Why am I saying this? Well, as you all know, there are two ways of doing mathematics. You have the rigorous way and the way that is used by 99% of mathematicians. So, of course, if you're a mathematician and you work in a natural language, you kind of trust yourself to write a proof that probably has many holes from a logic point of view, but you know, or step that you skipped, but you trust yourself to actually correct the proof and make it nice. If you're working in a formal language, well, from the verification part, it's much better because you have an automatic and perfect guarantee of correctness. The only problem is that you need to write a proof that is much more detailed. But if you work with a neural network, and I'll anticipate a bit on the talk, and let's say that you train your neural network by trial and errors, by reinforcement learning, and it gets a reward when you get the right answer. If you're using natural language, it's going to be first slower because you need human evaluation, but most importantly, we could arrive at a point where it's easier to fool a human than to actually prove something complicated in mathematics. So I think this really matters, and I'm going to come back to this later on. And so this is why I believe it's important to be able to design models in formal language. And the problem is that we don't have many data in formal language, for instance, so you could work with your favorite formal language. Here, I took Lean in my examples in the talk. If you look at Lean's MathLib, which is the main math library, you have around 300,000 theorems. This is the order of magnitude, I believe. So this is a large data set for humans. I'll never know like 1% of it. But it's a very small data set for training an AI model. It's particularly a large language model. So this is the limit of the approach. And so, how do we tackle this limit? Well, the first thing you can do is try to improve your process and say, okay, now when I give a statement, I'm not going to ask a large language model to prove it directly. I can first ask a small language model, to go fetch in the library the theorems that it believes could be relevant. And you give this as hints for your prover. I mean, if you're doing software verification and you're working with a solver, a SMT-based solver, so you can also give hints to the solver. So that's more or less the same principle. You can also leverage the fact that you have very good pre-trained models today, so there's no need to train from scratch a model, as was done in GPTF. And this was done in particular in this paper by Fabian Glöckler in 2023. What's nice about this paper is not really that it shows what you can do with it, it also shows what you can't do with it. Just to say that even if you do this, it's still not going to be enough. Your model won't be amazingly good. So you can try to then tackle the lack of data. The first thing you can do is try to get all the data gathered on the internet that you can find. So you essentially scroll the entire internet, and whenever you find some code in Lean or Rock, you take it. If this is still not enough, so then you can try to create your own synthetic data. So you're going to apply some rules to create, for instance, theorems that are correct, that are probably perfectly useless but are correct, and at least it's still some training data. But then a smarter thing you can do is try to actually do some automatic formalization. And so I'm going to detail this a little bit. Automatic formalization, or auto-formalization, as it is known in machine learning, is a natural idea from the machine learning point of view to get more data. We don't have a lot of formal language data, but we do have a lot of natural language data. So if we can train a neural network to translate from the natural language to the formal language, then we're happy, we have a lot of data. There is just one tiny hiccup, which is that this task of formalizing something is extremely hard. If you're in this room, I'm sure you're already convinced. Usually I tell people that there are researchers whose main area of interest is to actually translate. So it shows that it's really a very hard question. So why is it a so hard question? Well, the very first difficulty that comes to mind is that the proofs that we write in natural language, they skip many steps compared to the proof in formal language. Steps that we believe are either obvious or easy. And sometimes they are not obvious or easy. So sometimes there are even mistakes. I mean, actually, most of the time there are at least small mistakes. So this makes it already hard, but unfortunately the difficulty doesn't stop here. Because if you want to do this automatically, well, if you're given a statement and you provide a proof, you can check automatically whether the proof is correct or not, just thanks to the computer assistant. But now if you're given a statement in natural language and you want to translate it in formal language, how do you check automatically that the translation is correct? You can have a proxies for doing this, but you don't have any way of doing it with a perfect guarantee. It's even worse when you're translating a definition, because if you have experience in formalization, you all know that when you translate the definition, sometimes you can't translate it as the natural language definition, and even after, you need to provide a proof that it makes sense, which we usually don't do when we are writing pen and papers mathematics. So that's a hard problem, and so far the way it's done for math papers is by humans is the following. People usually try to extend the natural language proof in a very detailed blueprint, so a very detailed proof, with a lot of lemmas. Then from this detailed proof, you extract the dependency tree, and then you parallelize the formalization among humans. And this takes a lot of time. There has been amazing effort from the formalizing community in the last years for Lean and in the last decades for Rock. And so there were many projects that one can check, but usually it takes many human years just for one paper. So it really takes a lot of time, which makes me say that if we were able to do this kind of task, not only from a machine learning point of view, it will be a mean because it will give more AI data, but from a mathematician's point of view, that will be extremely useful because this would accelerate the formalization of mathematics. And we could even dream of a world where you could check the correctness of new mathematical theories on the fly. You put a paper on archive, it's auto-formalized. All the small mistakes are fixed because there will be small mistakes anyway. Or it will say there's a critical mistake, go back, and so this will be very helpful, not only for the reviewers. And I guess if you're in this room, you're convinced that this will be needed, that formalization is useful. But if you're not convinced that formalization is useful because you believe the peer review system is already doing a good work at checking the proof, usually no one believes that. Even in some of the most prestigious journals of mathematics, just like Annals of Mathematics, you can have papers that are wrong. This is a famous examples of two papers that strictly contradict each other. So they can't be both correct at the same time. And I think the first paper was retracted something like 15 years later. So it took a lot of time. So I'll end this digression about automatic formalization just by saying that this is an extremely quickly improving field. If you look at what was, just a year and a half ago in July 2024, people were essentially able to have a good statement auto-formalization, so only the statement, for Olympiad-style exercise, so extremely specific. And so I think the main teams were the Herald team in China, the Numina team in Paris, and the AlphaProof team of DeepMind. Then a year later, about in June 2025, there was a team who said that they managed to formalize 4% of the lemmas of statements in archive papers. So you might think that 4% is not much. 4% of archive is still a lot of data. But there was no proof involved. Then in 2025, there were also we started to see some open source models that were released to auto-formalize some data. And then later, still in June and then in September, there were two first archive papers that were completely auto-formalized by first MorphLab and then MathInc, which is exactly the same team, with very little human intervention. The intervention of the humans were to do the blueprint, the very detailed natural language proof, and then after, the model auto-formalized the well, I think so. I hope so, because so just to emphasize this last example, so for instance, they complete the formalization of the strong prime number theorem. This took them 3 weeks. They didn't start it from zero at all. They started from a partial work from Terence Tao and Alex Kontorovich that took them a year. But it still generated something like 25,000 lines of code and maybe more informative, more than 1,000 theorems and definitions. So if you want to check, this is what the dependency tree looks like of what they formalized. Want to be slightly careful because they reproved everything, but some of these points were already proven by the previous work. But nevertheless, I mean, it doesn't diminish the fact that it's a huge feat to be able to do this automatically, more or less. All right, so I'm going back to my problematic of data. So let's assume that we have a very good auto-formalization, that we can gather data on the internet. I still believe that if you want to have an AI model that is better than, say, 99% of mathematicians, it's still not enough. Why is it still not enough? Because if you want to address problems, very hard research level problems, you will essentially end up in areas where, in any cases, there are very few data available, right? Someone was telling me, you're going to have a hard time finding 50 million examples of the Riemann hypothesis. Well, you know, that's kind of true. So how can we go further than that? Well, the answer is by using reinforcement learning, so essentially treating theorem proving as a game. And so this is what I'm going to talk in this second part. And I'm going to start by presenting a work that we did with Guillaume Lampe, Marianne Lachaud, Thibault Lavril, Xavier Martinet, Gabriel Ebner, Aurélien Rodriguez, and Timothée Lacroix. So something that took us essentially 2 years. We started beginning of 2020 and it ended in mid-2022. And the motivation was really AlphaZeros and AlphaGo from DeepMind. You know, with AlphaZero in particular, they had a model that could train against itself, and then after 3 days of reinforcement learning, it was better than any human on Earth. So we thought, okay, let's play the math game now. So this is the math game. You have a statement to prove. Making a move is applying a theorem. So you apply a theorem. If you apply a theorem, you need to satisfy the assumptions. So there they are. You make a move, nothing to show. You make a move, still 2 assumptions to show. You make a move, nothing to show. You make a move, nothing to show. You won this game. Oops. Wow. That's the morning. So we thought, let's play the math game and let's do the same. And after 3 days, it will be better than any human on Earth. Right? We are very enthusiastic. Things didn't turn out this way, fortunately. Fortunately for my job. And why it didn't turn out this way? Well, precisely because playing math is much harder than playing chess, and this, I guess, doesn't come as a surprise. But there are 2 types of difficulties. They are mathematical difficulties. You know, when you're playing math, the number of possibilities for the next move is extremely large. I mean, you can postulate a new lemma, so it's nearly infinite. It's extremely hard to know automatically in the middle of the proof how far you are to succeed. You know, I'm showing you a statement and I'll tell you how hard is this statement. I guess it's already hard to answer for a human, but finding a way to do it automatically is really non-trivial. And then you have machine learning difficulties. The first one, and I think this is the main one, is the fact that if you're playing chess, you're playing a symmetric 2-players game. So you can start with many untrained AIs. You make them play against each other. At some point, one is going to win. And so this tells you that this way of playing is better than this way of playing. And so you can use this signal to train, and you can do this again and again and again. And you hope that the models are going to be trained and become better and better and better. Now, math is a single-player game. So if you start with many untrained AIs, you give them the simplest possible exercise you can think of, they're all going to try, none is going to succeed, and you still have no data. So you can't train. Right? So for this reason, you can't start with untrained AIs, untrained AI models. You need to start with models that have been trained in some sense. So that's why all the first part I discussed with the GPT models still make sense, because we need to start from non-zero. All right, so how did we do? Well, the way we did in this first work was to have essentially 2 models. One that was trained just like the GPT model at first, and then tries to predict what is the next tactic to apply. The second one tries to predict how hard it is to prove a statement. So, of course, at the beginning it's extremely bad, but you know, we hope that it improves with time. And then, if you have a statement, you can see all the possibility of the moves you can apply as a huge graph, a huge tree. So your goal is to explore this tree in a smart way to try to see if you can find a subtree where there is no leaves. If there is no leaves, it means that there is no goals, nothing to show. So it means that everything on this subtree is correct. And the way you will do this is, go at the horizon of the tree, at the end of the tree, where you stopped exploring, then select some nodes. Then you're going to use the first model to suggest possibilities of what you could do, and you're going to see what happens if you apply these possibilities. You know, what do you have to show? Then you're going to use the second model to say whether this is hard or not. And then you're going to backpropagate the scores, and at some point, from time to time, you're going to be able to actually prove something. And so if you prove something, you say, okay, this was the right way of doing. And then you can keep training your two models on successful proofs. So they become better and better and better with time. So, if you do this, what's going to happen is the following. What we obtained were models that were able to do exercise at an undergraduate level. Some exercise from, most of high school exercise up to Olympiad levels, national Olympiads. And then a few exercise from the international mathematical Olympiads. Okay, just like this one. It's not the hardest, but I like it because it's only in one line. So for any n, 7 never divides 2 to the power n plus 1. It's not very hard, but can let you think about it and can give you the proof otherwise. Of course, today the models are much, much better than that. I mean, this will be completely obsolete today. But remember that what I just showed you was mid-2022, actually beginning 2022. So there were no ChatGPT. Actually, even 6 months later, there was still no ChatGPT. So it was a prehistoric era from a language model point of view. So for this reason, we decided to do a more recent version in 2024. Which was, better AlphaZero start proof search in the era of pre-trained model. So it's essentially the same thing. I mean, we did change a few things in the reinforcement learning procedure, but I don't want to insist on that. But instead of training from scratch a model, we start from a pre-trained model that is fine-tuned just on one library. And then, when you use your reinforcement learning procedure, of course, you need to train by trial and errors on something, and this something is a state of statement to prove. And we were trying to keep this set of statements as small as possible because remember, we want to work in a low data regime to prepare for the day where you have to tackle some math problems where you don't have a lot of data anyway. And so what we obtained was a model that at the time was on par with the state of the art in Olympiad exercise because this is what people used a lot. Of course, today it's completely outdated. It was the state of the art of the hardest benchmark of the time. But the nice thing about that was that it used very, very little data in the reinforcement learning part. It used like 240 examples. Why do I say that 240 is not much? Well, if you compare to some people seems to believe that it's already a lot of examples. Well, for a human maybe. But if you compare to for instance, the models that become better than us on Potent Bench afterwards, I think they used 1,000 times this. And some of the more recent models they're using 10,000 times this. So it's not much compared to what is done usually. And so I believe the progress that were made in this paper were really different from the progress made with auto-formalized of synthetic data later on. Okay, so this was a first type of reinforcement learning that you can use. You're trying to find your proof, to search the possibilities and to find your proof step by step. There's another paradigm that emerged recently. It's the whole proof generation. You might have heard about it before because it made a company named DeepSeek famous. And then later on it was adapted by Kimna provers and the Kimna team and several others to formal languages. So how does it work? Well, the first step is you start with a model that already has good performances. I'll come back to this later, but this is important. Then you generate, you give it a statement, and then you ask it to generate k proofs. Okay. On these k proofs, hopefully some will be correct, some will be wrong. At least one will be correct. So what you do is that on the correct ones, you reinforce the correct ones relatively to the others, and you give a disadvantage to the other, or you give an advantage to the correct one. And then you do this again and again and again, and this proved to be extremely efficient. And so this gave rise to a new class of models. And I think we can note a few things. The first thing is that this emerged because the models had already become good enough. Because here in this step, if your model is not good enough, you might generate 100 proofs. If your model is completely unable to generate a whole proof without any mistake, remember, if we work in a formal language, like anything is, anything that is not perfect is a mistake. Then you will get only zeros, and if you get only zeros, you can't train anything. So I think the reason why it emerged in 2024 is also partly, and not 2022 or 2020, is partly because the models had already been good enough and the data existed for these models. They were relatively cheap to run. This kind of algorithm is relatively cheap to run compared to a proof search, so that's also made it very useful. But most importantly, you only need to evaluate the final answer. you only need to see the whole proof and then check if the proof is correct or not. You don't need to see if every step gives something that is valid or not. And this made a lot of difference. If you look at a proof search, you will try to find your proof step by step. So if you're trying to prove this, same small example, then your language model is telling you need to apply this step. Well, you need something that tells you that first applying this step is a valid move, and then that when you apply this step, you get something, and the something is this, right? So you need a computer assistant. And so when I told you at the beginning, we had a crazy dream about having AI that could prove mathematics, and we wanted to do it in formal language. Well, this is exactly the reason, because we had this in mind, and we thought there was no way we could do otherwise. But now, if you're generating the whole proof at once, you only need to evaluate the final answer, which means that you might not need for a strict formal system. You can imagine that you could train it in natural language. Of course, you can't check the proof in natural language, but if you are restricting yourself to the subset of problems where you need to construct a final answer, and if the final answer is correct, like for instance the right integer or the right function, then you have a good confidence that the rest of the proof is correct because you can't find it by mistake. Then you can train like this a model in natural language, and you don't need your formal system anymore. Of course, it limits the training, but the miracle was that when you do this, the model generalizes a bit. And this is at the origin of all the so-called reasoning models that you are hearing about today, GPT-5, Gemini 3 Pro, DeepSeek, and so on, Magistral, and so on. They are all essentially working this way. So, so this gave rise to many claims. So in particular from OpenAI, this is a post from Sébastien Bebek. So there were essentially several claims per week since September of OpenAI saying, GPT-5 solved this problem or this problem because the reasoning models are actually good at doing math. One need to be a bit careful with these claims, in particular this one. But still, I think we're forced to realize that there were several breakthroughs in the last few months that were essentially written by GPT-5. In particular, if you look at this theorem on the Nesterov-ODE, well, so they solved this question, which was an open question since 1983, and they essentially did it with GPT-5 Pro, and they even shared their chat if you want to check how they did. It's actually quite interesting. So they gave a lot of information to GPT-5 Pro, but at the end of the day, it's essentially GPT-5 Pro who solved it. Last week, there were a lot of fuss because Terence Tao said that, recognized that some researcher managed to find the proof of an Erdos problem only with GPT-5.2. So this kind of reinforcement learning is the reason why these models have become so good at mathematics. So because we wanted to see a bit more clearly about that with two students, we decided to do a benchmark that I hope will be live this week, which is a benchmark of lemmas that you extract from archives. So you go on archive, you take the last week, you look at the math papers, you extract some lemmas, and then you ask a model to prove this. Then you ask another model to try to judge the proof, and then you ask humans. So you take the ones that succeeded, and then you ask humans what they believe what they believe and what they think of this proof. And so the number have to be taken with a lot of caution because they are still evolving. I think that's why the paper is not online yet. We still have to do one run. But it looks like essentially 7% of the time, both the humans and the LLMs agree that the large language model managed to show the lemma. 7% is very far from being 100, but it's also very far from being 0 because we're talking about research problems that are actually uploaded on archives, so actually done by mathematicians on a daily basis. All right, so this raises a question, do we still need formal languages in AI for theorem proving? And I deeply believe that the answer is yes. Why? Well, because I think we are here. So I think these models have already become better than human average on literature review. They start to be comparable with human level reviewing of the correctness of human written papers. They are already good at proving lemmas and systematically proving some small theorems and lemmas correctly, and from time to time a big theorem, a better theorem. And I think very quickly we're going to have language model in natural language who are good at proving theorems essentially as an average mathematician. But the problem is that we won't have any guarantee of correctness because this will be in natural language. And these models are becoming better and better at doing mathematics, but they are also doing better and better at doing mistakes that we are unable to spot. So I anticipate that there is a world where we could have a small crisis in the coming years in the math community because of these proofs that where people didn't realize there were some mistakes. I was discussing with an editor of one of the main math journals, which is Inventiones Mathematicae, who was telling me that they received a proof of theorems that seemed amazing with a proof that was completely wrong. And the authors didn't even realize it, and it was completely written by GPT-5. So I believe we really need at least a good auto-formalization or an acceleration of formalization, because we will need to check the guarantee of correctness. So I think it's important to train models in formal language. All right. So now how do we go beyond these two types of reinforcement learning I discussed? Well, if you think about it, generating a whole proof at once, and then saying, if anything in this proof is wrong, I discard it, that sounds a little bit suboptimal, right? So one thing you can do, this is something we did with Fabien Glöckle, Alex Gu, and Gabriel Signeff, but there was similar approaches, different similar approaches by different teams, is the following. You could say, okay, now instead of generating a whole proof at once, I'm first going to try to generate a skeleton of the proof, and then I'm going to try, I'm going to have a prover that's going to try to prove the different parts of this skeleton. So this was something that, this is an approach that dates back already from 2022 by Albert Jiang at the time. But the nice thing you can do is that if you decompose like this, you can train both the sketcher and the prover at the same time in your reinforcement learning loop. And if you're doing this, you hope to decrease the complexity. And if you look on this figure that doesn't say much, because I'm talking about cumulative solve rate of our benchmark, but I don't tell you which benchmark. You can see that if you're doing this sketch and proving thing, at first you're not doing as well, but you saturate much far away than the GRPO baseline or the different variants of GRPO that you can find. So this actually improves. Okay, so I hope I convinced you that this was a field that is evolving extremely quickly. But if I didn't convince you yet, we can just take a step back and see what happened in just 6 years. So 6 years ago is when I started looking at this field myself. And at the time, essentially the best thing that an AI model could prove was essentially this kind of theorem. That's a one-liner in most formal language, in the most computer assistants. So it's not the theorem of the year. Fast forward a few years later, in 2024, the models get a silver medal at the International Mathematical Olympiads in formal language. In 2025, the models start to have close to human performance on some problems in natural language and a gold medal at the International Mathematical Olympiads in formal language. So things have been changing extremely quickly, and I'm very curious to see what's going to happen in the next 6 years. So this is the end of my theorem proving part of the talk. Now I'm going to discuss very briefly how this could transfer to software verification. So of course, theorem proving of mathematical statement in a formal language is relatively close to software verification. There are a lot of similarities. A non-negligible difference is that in some sense math proofs are easier. Math proofs are written in a functional programming way, and they're relatively flat. I mean, okay, you can have loops, but those are control exceptions when you have a guarantee of termination anyway, if you have inductions. So in software verification, the situation can be a bit more complicated. In particular, if you look at imperative programming, I mean, okay, we all know it can be faster than functional programming, but it's also harder to verify. Okay, of course, if you're familiar with Hoare logic, you can reduce this task to providing specifications and finding invariants most of the time. And you have several SMT-based frameworks that exist. I guess one of the most famous is Daphne. But when the automation fails, it's not always easy to fix this by hand, because you don't get often, you don't exactly know where it failed exactly. So one thing you can do, one question is, can we transfer all that we said and move it to this? Well, one thing that was done, one approach that was done by Mantas Bakshis, Fabien Glöckle, Darius Ferrer, and Kunao Zhang, and several other co-authors in 2026, So it's a paper that is not online yet, but I guess it will be in a few weeks from now. The procedure is the following. You can leverage the fact that Lean supports monadic embedding of imperative code, and so that you can work in Lean, and for this you can use your favorite monadic embedding. Then you can use the LLMs to provide invariance lemmas and solver hints. And then you can use your SMT solver, and if you didn't manage to close all the goals, you hope that the Lean automation based on this will close the rest of the goals, and if not, at least you get a feedback of where it failed. When you are using your LLM, you can do this in several ways. You can either use just a single LLM, a linear way. You can have a multi-agent approach where you have several LLMs trying to provide, each provide lemmas or change in the method implementations, but they have a shared state file, and then you have a judge that says, okay, let's merge this one or this one. Or you could do exactly what I discussed 2 minutes ago, which is doing some sketching and proving. So you have something that derives the sub-goals and then something that fills in the sub-goals. So I think it's a way to bridge what I just discussed and software verification. Again, because it's not a paper that's online yet, I can't discuss much the results. What I can say is that this seemed to be a very efficient approach. In particular, on the Clever benchmark, they went from 8.5% to more than 30%, which this used to be the state of the art. And this, I believe, is only the beginning of this kind of transfer of technology. I think I'm nearly over time, so I'm going to conclude. I hope I convinced you that AI and LM for theorem proving is probably only the beginning, that these techniques might be helpful for software verification too, or I believe actually they will. I clearly believe that LLMs and reinforcement learning won't be the final AI tool that we use in mathematics. I mean, reinforcement learning for sure, but LLMs maybe not. But for now, it's still a very good tool. I clearly believe that the practice of mathematics will change. Usually when I was presenting to mathematicians, I would try to hide this line, but now I think like I'm confident enough. Yeah, and I think that's okay, because I don't think AI will replace mathematicians and instead enhance them. There are many fields of mathematics in the history of mathematics who disappeared when the technology changed. Well, I mean, we moved on to even better fields. So on this, I'd like to thank my co-authors. Usually I try to post some pictures, but I was afraid of the copyright policy of the ACM, so you just have the names. I thank you for your attention.
Thanks a lot, Amaury. So we have plenty time for questions. I hope there will be. So the mic will come from the back.
Hello. I think it's good now. Yeah. When I started to be interested in these formalization of mathematics, and I met people at Princeton on this topic, there was a paper by Good that was explaining that the main activity of mathematicians is not about doing proofs. And so here your talk is mostly concentrating on the proof activity. Is this the place where the human activity of mathematician is going to concentrate, the non-proof part of mathematics?
I think so. So that's also why I think it's okay. Essentially, yeah, I feel like there are at least three different activities in mathematics. You try to conjecture what would be interesting to prove and what might be correct. Looking at some small examples to get some idea of what's going on and try to understand construction, and then proving theorems. Most of the machine learning effort was concentrated on proving theorems, and as you say, indeed, that's far from being all mathematics. So I believe that this part will be accelerated, and that we will be able to spend more time on the other ones.
Yeah, but there's also the fact that you look at a phenomenon in the real world, and what can mathematics say about this phenomenon?
Completely.
And this discussion with the real world is a place where it's completely not formalized.
Okay. So, okay, I will tend to agree with that. There were a few approaches in particular in symbolic regression, where you try to give some data of what you observe in the world and you try to have a model deriving the equations for you. It had some success in places, less in others. So, but I feel there is also an effort in this direction, but I completely agree with you that the essentially modelization of the world and modeling of the world, and which I kind of included in the small examples, is also something where we're more or less safe, if I place myself from the mathematician point of view. It's funny, but because of this, I remember that there were some applied mathematicians telling me, okay, that's the first time I'm very happy to not be a pure mathematician. So I think it kind of answers the question.
Very interesting talk, thanks. So for the first two examples, you mentioned the first two strategies that you described. You mentioned that it was useful to have intermediate steps in the proof assistance, that when you do one step, you have a goal that changes, and you can use that to generate the next one, and so on. So it seems that it was important to have this kind of design where you have intermediate steps that Rock and Lean have, but maybe not other proof assistants like Ecole Light, where you would go more forward and you don't have explicitly those steps. And so you also, maybe that also constrain your space generation. But then you mentioned that turns out we can do whole proof generation. So this kind of disappear. So my question is, do you think that the specific design and features of the proof assistant matter a lot or not really?
Yes, yes, I think it matters a lot, and not only for this reason. So for several reasons. First, the way you express something in your formal language, in some formal language it's extremely, most it's extremely hard to do some PDEs, but in some it's harder than others. So this would bias you toward the field of mathematics you're looking at. So it will definitely create some difficulty. Another way of influencing a lot is the automation that already exists or in these languages. For instance, I kind of think that the reason why I'm not 100% sure about the reason why Lean emerged and when was chosen by the machine learning community instead of Rock. I believe that for Isabelle, the reason was that at the beginning, Isabelle automation, it was already extremely good. And so you couldn't compare yourself to Isabelle automation with any language model. And so people, yes, okay, so this thing is too strong for me. Let's move on to Lean, where there was no this automation. So I think for good and bad reason, it did constrain us, yes.
Thanks for the talk. So you drew this distinction between formal statements that you don't have enough potentially to train large language models, and then you compared it to the informal statements. But I'm always wondering, are there actually enough informal statements to train a large language model? Because there's also this social component of what you consider a meaningful statement and so on. And I was thinking that's probably a few million, but potentially that's not even enough for a large language model.
That's a very good remark. The answer is no, indeed, it's not enough, but it's still better. Someone made me realize recently that actually Archive is not that large, but if you take all the math books that exist, it starts to be close to what you need. I think in any case you need reinforcement learning on top of that, but the distance you still have to do after your first fine-tuning really depends on your amount of data. And with informal statement, that's already a lot more data.
Okay, interesting, thanks.
Thanks for the talk. I want to follow up on the automation question. So in those approaches, typically the automated theorem provers that exist today and that are the grounds for the good of automation, Isabelle or other provers, they are not used as far as you have presented it, it seems. Should it be like that? Should people try to combine these communities?
Well, to be fair, at the beginning they were used. And if you look just at the GPT version of proving theorems, and you look at the first proof that were released in Lean, this was like, the first proofs were like library search, simple. It was funny because at the beginning on the benchmark that everyone was using on Inner Olympiads that was called Mini F2F. So people started with like 30% accuracy. So now it's the end. It was 99.9 last year, but people started with 30% accuracy, and then someone realized that if you just do a combination of the four automations, main automations of Lean, you actually get 33%. And then they realized that the average length of a proof given by language model was like 1.7 step, which kind of showed that it essentially learned only to call the automation every time. I think they are still used in some of the. They are seen as a tactic that you can call from the language model. So I think they are still used. I've seen the reverse version, meaning that in Lean, in the Lean hammer, there is a version where you can call a language model. So I think yes, it's good to combine, and I think the language model starts. Since a little more than a year, they have a level that is high enough to start to be better than the classical automations, and so that they could be combined. Before, I feel like the automations were essentially better anyway.
Hi, very interesting talk. Thank you. I have a question because I've been thinking about. I'm not at all in the domain of machine learning, but I've been thinking about how machine learning could be useful in what we're doing. And one of the tools that we're using every day when we are proving programs is our SMT solvers. And I've been thinking about how to improve SMT solvers using machine learning. And the reason for this is that actually an SMT solver is a software which is a pile of heuristics. There's like millions of heuristics applied every second when you run an SMT solver. And my intuition was that it should be possible to use a neural network or some to train a neural network to find the right answer to these heuristics instead of using well-tailored heuristic that not always work.
That's a very good question. So first, I think yes, there will be something to do with SMT solvers, and there are a lot of people wondering actually with SMT solvers and with set solvers about what you can do to help. With SMT solvers, but typically the example I showed on software verification is trying to give some hints to the solver to have it work for those who support this. So I think this is a first way of doing. It's a bit. One need to be careful about replacing really I think you can train a model, try to derive better heuristics, but or try to give hints to a solver. It's really hard, I think, to replace directly the SMT solver, but at least by a large language model, because the large language models are very slow to run. So that's I think is the main limit and the main reason why people still use a lot SMT solver. It can be a good and bad point, but because the time they need to run doesn't really depend on the complexity, because they look in the symbolic domain. So it depends on the size of what you try to input and the size of what you try to output. For this reason, in other applications of large language models to problems that are explicit resolution of some problems in math in 1D, 2D, 3D, for the language model it doesn't really change 1D, 2D, 3D. For the math algorithm. Usually you don't do 3D and you're happy with 1D. So yeah, I think the limit will be the execution time of the LLM, but there's definitely something to do.
You don't need to use an LLM for doing this.
LLM, but you will have the execution time of you could train a model. You need and I'll say you need to restrict to a smaller model because you really need to have something that has a few million parameters might be relatively long to. Even transformer with a few million parameters, it can already be a bit long to output something even on 8 GPUs. Say.
Thanks for the great talk. At one point you mentioned generating proofs in informal languages with verifiable answers as a key stepping stone in the DeepSeek prover and Kimina prover style training. Do you still see this as remaining an important stepping stone in the future, for example, for software verification?
Okay. I don't think so for software verification, because I think like in software verification, by definition, you work in a formal language. So you can always verify, I mean, you can always look if your verification is correct or not. For Kimina, they did use the fact, they did check the whole proof, not just the verifiable answer. It was important in natural language. Because in natural language, you'd like to have a proxy of, I check the proof. Then you have essentially two possible proxies. Or you ask a large language model to check the proof and you believe that this is the answer. And you need to be very careful if you train in reinforcement learning like this, because you might train your model to actually fool the other model. So or you check the final answer because you are restricting yourself to an area where you just have to check the final answer. It's not clear whether it started like this. It's not clear whether the last models of GPT and Gemini were also using some formal verification, some partial formal verification to verify just maybe some of the steps as a safeguard, or try to formalize just the final answer or something like this, because we don't have any details. But that it could happen that this had been the case, and I believe it will be interesting to add more formalization. But as we said, it's relatively hard when you start from the natural language part.
I just wanted to maybe push back a little bit on the software verification only happening in a formal tool. This is not necessarily the case.
Okay.
Before these formal tools existed, people were doing hand proofs.
Oh yeah. Okay. Then that will be the same, I guess. Sorry.
Thank you for your talk. So there is another kind of game which is played by mathematicians where you're trying to combinatorially classify something. Like it could go from graph to isomorphism or finite simple group if you want something complicated. And usually the game is there is one people which try to find a new example, and the other one try to show that these examples are isomorphic to the known one. So it's a kind of a two people game, adversary game. Do you think AI could help like that? Like one computer inventing new example and the other one, no, it's already known? I don't know that.
I think that would be a very interesting game to try. Yes, I think so. I mean,
some example.
I knew not the classified version, the one where you try to construct new quantities that maximize some score, or that, like, for instance, you have we're looking at Sidon subsets, for instance, so you try to maximize the score. So these, I knew a lot of approaches that were doing this, but the two players one, I haven't heard about it yet. I think it will be very interesting indeed, because it's quite adapted.
Cool.
Hi, thank you for your talk. I'm a first-year PhD student, and the story you're telling makes me think that in 2 or 3 years I might be just able to generate everything automatically and solve my... so I might just lean back for 2 or 3 years and hope for the best. But wouldn't that be disingenuous? It's a soft question, but...
No, it's... So...
How much of my PhD thesis would be me, and how much would be co-authored by?
Well, I mean, I've wrote my PhD thesis in tech. I don't especially believe that tech co-authored my PhD thesis, though. So, no, but I mean, okay, that's said as a joke, but I think that's a very relevant question. That it's good to start trying to work with these models, but I think it only changes the horizon of what you can achieve. I think it starts to. I think the models are not completely ready, but they will be I think they will change a lot of things in 1-2 years from now. In mathematical proving, in particular, in theorem proving, I think it will be a bit a waste to do yourself some small technical steps that now AIs is doing extremely fast. I still have myself sometimes trouble in leaving this to the AI and then checking. In particular because it's not as fun. But on the other hand, I spend more time on some very fun parts, and I'm a bit proud when I give something to a very strong AI model and it's completely unable to prove it, and I know how to prove it. So I'm not sure it's going to last for long, but...
So that's time
Hi, thank you for your talk. So what should be the workflow nowadays when doing proofs? In the sense that I write a statement and then at that moment I let an LLM to prove it, or should be something that happens in the background and maybe have some kind of script that tries 10 different AIs? What should be the workflow nowadays?
Well, the day the AIs will be good enough to try to verify themselves a bit better than they are now, you could start having indeed the 10 different AIs that write in the background, and something they all try 10 times, and then something tells you, filters, and then gives you the best. This is still going to take a lot of time, because if you look at the most advanced reasoning model, to give you a good answer, they need like 10-15 minutes. So it's not like you can query them 25 times an hour. My very personal way of approaching this right now, but it's very personal, is usually I asked a language model, especially when I want to tackle a problem that is new to me and not completely in my area, I ask it to do some kind of literature review of, with a few hints of what I believe could be a good orientation for the proof, and then I quickly get an idea of what people tried so far. And then I usually try to do it a bit myself, and when you have good ideas of how you think the proof might work, usually they are good at telling you whether it can work or not. From time to time they completely fail what is feasible, but other times, I remember very recently I wanted to prove something, and I said, okay, I have a very good skeleton, I'm giving it to Gemini DeepThink, I think it was Gemini DeepThink, and he answered a proof with an additional assumption. So I said, okay, forget about the additional assumption, I don't want this. Then he gave me a weaker assumption. I was like, no, forget about it. And then it answered, okay, but without this assumption and with your skeleton of proof, there's no way it works, this is why. And this was correct. So I think in this direction it helps me. Yeah. But it's very far, I mean, nowadays it's still very far from replacing your work of mathematical proving. It's just allows you to not spend some time on things that are more or less known or classical. That's it.
Okay, so I guess it's the final word for this morning talk, and let's thank Amaury again.